In the previous video, we have discussed the notion of least upper bound, that is the supremum of a set. Okay, that is the least upper bound, and the infimum, that is the greatest lower bound. Okay. Now, one thing I want to point out is if the supremum of a set E exists, then it may or may not belong to the set E. Okay, alpha may or may not belong to E. So alpha belongs to E, or alpha doesn't belong to E. Of course, it will be only one of the two cases every time, but both possibilities are possible in principle. Okay, so let's say, for example, let's define E, which is the set of rational numbers, okay, such that the set of negative rational numbers. Okay, and let's say, let's call this one E1, and let's do one that is very similar, that is the rational numbers that are non-positive, so that are less or equal than 0. Okay, okay. So in both cases, the supremum, so the supremum of E1 is going to be 0, okay, and the supremum of E2 is also going to be 0. Okay, the problem now is that 0 doesn't belong to E1 and 0 does belong to E2. Okay, so you see that we can have both cases. Here we have an example where the supremum belongs to the set, then we will say it's a maximum, and another example where it doesn't belong to the set, and then it's just a supremum. Another example, let's say we have E, that is the set of all numbers of the form 1 over n, where n is a natural number. Okay. So what is the supremum here? So we can plot it if we wish. So they are all going to be positive, and then a 1 over 1 is 1, then 1/2, 1/3, 1/4, and so on. Okay. And it will kind of accumulate towards 0. But 0 is never going to be part of E. Okay. But now, what is the least upper bound? What is the supremum of E? The supremum of E is equal to 1. Is the smallest number that is bigger or equal than every number in the set E. Okay. We take any number below 1 and we are already leaving one member of E out. So the supremum is equal to 1. And in fact, 1 is a member of, it belongs to E. But if I take the infimum, the greatest lower bound, so the greatest lower bound is going to be 0. Any number to the right of 0, and I will be leaving out most of the sequence. So 0 is the largest I can pick, but 0 does not belong to it. Okay, so again, we see this dynamic. Now, this is a property of a set, that the bound is inside the set or not. So we are going to define that. We are going to give it a name so that we can use it. So let's say that S is an ordered set. Okay. It has the least upper bound property if, well, if the following is true. So if E is a subset of S and E is non-empty, okay, this circle, this crossed circle means empty set, the set with no elements. Okay, E is not empty, and E is bounded above. Okay, then the supremum of E exists in S. Okay. So again, here we say that an order set has the least upper bound property if for any subset that we pick, whatever subset we pick, then we can be certain that that subset is always going to contain the supremum. Okay. So notice that this is for every choice that we make of the subset E. It's not okay if we say, well, I found one subset E for which this works, I'm done. No, it has to be for every single possibility. So we know already one example of a set that doesn't have this property. The rational numbers do not have the least upper bound property. Okay, why is so? Well, for example, we have here, we have here the example E1. Okay, this is a subset of the rational numbers, and it doesn't contain the supremum. Okay, we also saw in a previous video the example where we took the rational numbers Q that were positive and whose square was smaller than 2. Okay, remember? So it went something like this, and it was all these numbers here in between 0 and square root of 2 that were rational numbers, leaving out square root of 2 and 0. Okay, so this A is clearly a subset of Q. Okay, the supremum of A is a square root of 2 that is not a member, is not an element of Q. So that's it. This is a counterexample that shows that Q, the rational numbers, do not have the least upper bound property. Okay. Now, the next question that anybody should have right now is, okay, so what? What is this definition useful for? So there is a very close relation between greatest lower bounds and least upper bounds. Okay, and from there we will see what's the utility of all this. So let's say, so we have our greatest lower bound on our least upper bound. Okay. So what happens with this? So every set that has the least upper bound property also has the greatest lower bound property. Okay, this is just in case someone was thinking that we should also consider the 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 greatest lower bound property. There's no point because you have one, you have the other one too. This is a theorem, but this we will cover in the next video with the proof.